Hello, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is gas power cycles. The sections in the textbook in Sengel and Bowles are sections 9.1 to 9.4. Alright, there's 4 learning outcomes for this video. First, what we're going to do is we're going to define what the thermal efficiency is of a cycle. We're also going to discuss relating the Carnot efficiency to this general thermal efficiency that we just defined in the first point. Make sure we understand what is the air standard assumption, and then we're going to review several gas power treaties. So first, I want to go ahead and discuss thermal efficiency. And remember, mechanical engineers are interested in one particular thing in thermodynamics, and that is we want to be able to determine how well we can turn heat into work. And in terms of symbols, I like to draw it this way, that we are doing a Q into a W transformation. So this is pretty much what mechanical engineers are interested in, and a lot of what we're going to be doing in the first few chapters is looking at details of how efficiently we can turn Q into W. Now, one of the things you might remember from the second law of thermodynamics says that we cannot do this with 100% efficiency. If this is Q coming over here, represented by this large arrow, and then I want to go ahead and convert that into work. What we learned in basic thermodynamics is we cannot convert all of the Q into the W. We're going to go ahead and have to reject some of the Q, the remaining Q. So let's go ahead and call this Q in and this Q out. We're going to go ahead and have to lose some of it in this somewhere else. And then this will be the net work that we're able to go ahead and convert. All right. So if we think of a device that goes ahead and converts heat into work, this engine over here that I show on the right would be an example of one. And so the heat addition, well, what that is the burning of the fuel causes this to be hot. So we can kind of think of that as the Q in, which is the fuel that is being burned. As this turns, it's going to generate a torque. It's going to go ahead and do some work. And there would be the net work coming out of this engine. And since we know from the second law of thermodynamics, we're going to be having some heat loss as well, and what tends to happen is that the engine gets hot, we run a coolant through there, and there is going to be the Q out. So this is our engine, and we have to talk about heat engines as a general type of energy conversion device, and this would be an example of more or less a heat engine with some assumptions that we will go through in a little bit. All right, now we want to talk about efficiency here. Now remember, efficiency is desired over required, and we use the symbol eta or efficiency. And so what is desired from this device is the net amount of work that we're producing. So it'd be the net work, and then we're going to normalize that by what is required, which is the heat that goes in. So there's my efficiency, the net work over the heat in. And if I do a first law energy balance over this little dashed line that I just saw, I can go ahead and eliminate the net work and find out that this is equal to 1 minus Q out over Q in. And what we can see from this equation is that the efficiency is going to be highest if we have a small Q out or a large Q in. So effectively what we would like to do is reduce that Q out. But what we do know is that we cannot completely remove it. The second law of thermodynamics told us that. And so this right over here is always going to be less than or equal to 1, and it will always be greater than or equal to 0. All right, so I can go and write it this way. Eta is going to be less than between 0 and 1. And this is what I'm going to define as the thermal efficiency. And we'll be looking at the thermal efficiency of many, many cycles in the next coming chapters. All right, I want to discuss a little bit about ideal versus actual cycles here. And so, for example, what I show on this slide right here would be this is a PV diagram, and I've got a cycle because I'm kind of going from one point and then I'm returning to it. So I've got these 4 states. These are ideal states. We've got a pair of intensive variables. My pair of intensive variables are a PV pair. Those are always independent regardless of my material. And so I can go ahead and maybe number these states as 1, 2, 3, and 4. And maybe I'm going in this direction. So this would be a power generation cycle, for example. And so I'm going around and I'm returning to my initial point. And so this would be a cycle that I have. And so I'm defining that there's kind of 4 distinct points that I have. So for example, let's say that this point 1, this is for example maybe a piston cylinder. It has a relatively large volume from the cycle, so this would be point 1. And then what it does is it goes to point 2, it's got some sort of compression. where the volume is decreased. So this would be 0.2. And then it's going to go to 0.3 where the volume remains the same, but the pressure goes up. And so there would be the same volume, but maybe it went, the pressure went up because we added some heat, which is typically what happens in power cycles. So there would be 0.3. Now as I've drawn it, I've got this one step that's nice and smooth, and then it kind of stops at 2. So the piston went down, came to a complete stop. Then I began adding heat, and the piston never moved. It went straight up. Well, that's clearly an idealization of what happens. If you think about when an engine is working, this kind of speeds up, and as it slows down, the fuel begins to burn, and so it hasn't completely stopped, and the volume changes. And actually, if I was to go ahead and draw the cycle, let me change my pen color to something a little different when I draw on here. It actually might look something like this, right? So it sort of rounds out the whole thing. And there would be my actual cycle. Right? So there's the actual cycle, and what I have shown before would be an ideal cycle. Now what we're going to realize is that it's a lot easier to analyze ideal cycles because we can go ahead and look at these particular steps where things are held constant, a lot easier to solve it thermodynamically. One of the things to recognize is it's always going to be an approximation of the actual cycle that's going on. And what we're going to do is try to minimize the discrepancy between the green curve that I show there, and then the ideal cycle that we had in red. All right, let's talk about the network of a cycle. All right, so here I got another cycle. This is a PV diagram, and the points are labeled 1, 2, and 3, and 4. And remember that the work when we're doing is always the integral of a force through a distance, or what becomes the integral of a pressure through a volume. And so we could talk about the work going from 1 to 2. Well, there's no volume change, so there'd be no net work from 1 to 2. If I look at it from 2 to 3, well, the integral of PdV from 2 to 3 would be the area of this large rectangle right there, going from a 0 pressure up to the top. And then if I look at it going from 3 to 4, I'm going to have an additional little area, sort of this trapezoid, that I'm going to add in as well. And then to complete the cycle, I'm going to go from 4 to 1. And now the volume is going to decrease, and so then I would need to go ahead and subtract out the area there. So quite clearly, the net work of the cycle, right? The net work is that little purple area in there. And so schematically, we can see exactly what the net work is. And so what we're trying to maximize net work, what we're going to be doing is trying to kind of maximize the area that we have in there. Well, what we'll also realize is it's going to be pretty convenient. Instead of always drawing PV diagrams, would be to, for example, to draw a TS diagram where we have temperature and entropy here. And so this might be the corresponding 4 states that correspond to these 4 states here. So there was point 1, and 1 to 2 was this constant volume process where the pressure went up. And as we said, that could happen by maybe adding heat. And so if we add heat to a system, the temperature goes up and the entropy increases. So this step from 1 to 2 on a PV diagram might be this step 1 to 2 there. And so I've got all 4 of my states marked over there. And again, if I knew what P and V were, which were an independent pair, I could always go ahead and determine what TS were at the corresponding states. Well, one of the interesting things is that the area underneath this TS curve is going to have the same area as the PV curve. And so if you're kind of, wondering why that is, well, remember that from the first law, du, some small change in the internal energy, is going to be del Q and del W. So for whatever heat I add and whatever work I add. I'm using del's here because these are path dependent, and a D because internal energy is a function, or not a function, it's actually a property. Right? And if I was to go ahead and want to know what the total change is as I go through the whole cycle, so I'm going to go ahead and integrate. I'm going to integrate from point 1 all the way up to point 4, or I guess I'm going to go all the way back to 1 again. So I'm going to 1 to 2 to 3 to 4. Integrate over that whole cycle. Well, what I'm going to have is that's going to be the total change in internal energy going from 1 to 2 to 3 to 4 and back to 1 again. Well, it's at the same state, so that's going to be equal to 0. And that right there is going to be equal to, well, it's going to be equal to Q plus W, the net amount of heat that I add, and the net amount of work that I have. So what we see is that the net work produced is going to be the same magnitude as the net heat if I'm going through a cycle. So W net is equal to Q net, right? Well, now also remember that ds is equal to del Q over T. This came from the definition of entropy, and if I go ahead and rearrange that, I have del Q is equal to T ds. And if I go ahead and integrate both of those, all I'm going to have, right, is going to be T delta S is equal to Q. And so if I integrate this whole area underneath here, so I'm integrating 1 to 2 to 3 to 4 on the TS diagram, I'm getting Q net, and Q net is the same as W net. So what's interesting is that this area that I have on the TS diagram is going to be the same as the area that I have on the PD diagram. So it's going to be a pretty useful tool, because sometimes it'll be easier to look at a TS diagram and recognize that, again, we're trying to maximize the area on the TS diagram. So then what we're doing is maximizing the network. All right, let's discuss the Carnot cycle. Now, remember, the Carnot cycle is this ideal cycle that has 4 steps. It has 2 constant temperature steps. In this diagram, we're shown 3 to 4 and 1 to 2. And then 2 isentropic steps, which is this 4 to 1 and 2 to 3. Isentropic, remember, means delta S is equal to 0. And so this is shown for an ideal gas. You could also draw the Carnot cycle for non-ideal materials, but it's typically shown here in an ideal gas. And as we just discussed, since this is a PV diagram, the area in here is the net work. And the Carnot cycle, remember, generates the maximum work. So this area in here, this W net, is going to be the largest of any cycle that I could potentially have. If I look at the corresponding cycle on a TS diagram, so again the Carnot cycle, my isentropic steps, for example, is 4 to 1 is now straight up and down because entropy doesn't change. And so I've got this nice kind of constant box because temperature is constant, so it's straight across, and the area underneath here is also going to be the net work. Right? Well, this is the Carnot cycle, so the net work of a Carnot cycle is always going to be the largest that I can have. And actually what I want to do is erase what I just wrote on there. So I'm going to draw on this diagram a little bit. All right. Now an actual cycle, right? So maybe let's look at the step 4 to 1. This is this compression cycle. In an actual cycle, it may not be completely isentropic, and maybe we generate some entropy, so we might go to that point. And then we're going to go ahead and we've got this power stroke that's going across here. I'm adding some energy, for example, but maybe the temperature goes up, and so I end up at some point right there. And then I've got a power stroke coming down. It generates some entropy that I'm going there, and then dropping down here. So just kind of making some stuff up here. But one of the things we recognize is that this, if this is the actual work, right, it's always going to be smaller than the Carnot cycle, operating between the same T high and T low limits. And we'll be looking at this in more detail. But what I realize is the area underneath here of my actual work is always going to be less than the Carnot work. And so there we can go ahead and define, which would be, for example, a second law efficiency, which is going to be the work of the Carnot cycle, which is that large box, over the work of the actual, right, which is going to be always somewhat smaller, and we'll realize that is always going to be less than or equal to 1, or be greater than 0. And this gives me another metric of how well my cycle is operating versus the Carnot cycle. Now this efficiency is different than the thermal efficiency. This is the second law efficiency. But we can go ahead and relate the two. And this is often more useful because if we had a perfect cycle that in theory we could have an efficiency of 1, which would have the corresponding thermal efficiency of the Carnot cycle. All right, now I just kind of want to go through some definitions. And one of the things we'll be discussing in the next couple of videos when we start looking at power cycles, like Otto cycles and diesel cycles, is this something called the air standard assumption. This is just a series of assumptions that make analyzing the cycle a little bit easier. Okay? So first of all, the first one is that we're going to assume the working fluid is an ideal gas. Usually this is air. And so for example, this might be air with a little bit of fuel in it, a little bit of gasoline, but since it's at such a low concentration, we can go ahead and assume that it just operates as pure air, and air under most conditions, even the high pressures that we have in engines, is an ideal gas. We're also going to assume that all steps are internally reversible in the air standard assumption. That means we don't really have any friction going on in there. It's not necessarily externally reversible, just internally reversible. We're going to go ahead and model the combustion as heat addition. We're not going to be looking at combustion at this point. So what we can think of is the burning of the fuel is just like there being some amount of heat Q that's going into our engine. We're going to model exhaust as a heat rejection. So we'll just have that as heat going out. And so that would be the exhaust of the burnt fuel. We'll just look at it as heat leaving the system. And that's it. Those are the four air standard assumptions. All right. Now we kind of want to go through a little bit of terminology in engines, and so we're looking at reciprocating engines here, like Otto engines and diesel cycles, which we'll be looking at in the next couple of videos. And so just a little bit of terminology. There's something called TDC and BDC. This is top dead center, bottom dead center. And what that means, if this I have is a cylinder, and I have a piston that's going up and down through here, and I've got these inlet and outlet ports on my engine. Top dead center is the point at which the highest point that the piston head will go. Bottom dead center is the lowest that it will go. And then what happens as it operates and reciprocates, it goes back and forth between top dead center and bottom dead center. The stroke is the length that it's going between top dead center and bottom dead center. And the bore is the diameter that I have across here. So I have the stroke, and then I've got the bore, which is the diameter. And this is normally a cylinder, so it's actually got a circular cross-section, and the bore is the diameter of that cylinder. The clearance volume is the amount of volume that doesn't ever get expelled, and so that's the difference between top dead center and the very top of the cylinder. So this right over here that I've shown, that's the clearance volume. The displacement volume is this one right here, which is the volume that's actually getting displaced as I go between top dead center and bottom dead center. There's something called the mean effective pressure. And so let me kind of mention what that is. And so let me just draw a little small PV diagram and little power cycle, kind of like we had before. It might be this on a PV diagram, going through my, for example, 4 states. The mean effective pressure is going to be a pressure that, if I was to go ahead and draw this, where this right over here is my displacement volume on the bottom, the area of that is the same as the area underneath here, and that pressure is the mean effective pressure. So if I multiply the mean effective pressure by the displacement volume, I'm going to get the same area as W net of the entire cycle. So that's what's called the mean effective pressure. A couple other things. Spark ignition are often called SI engines. These are Otto engines where you actually have a spark plug, and that's in contrast to a compression ignition or a diesel engine where ignition occurs simply because you compressed it to such a high temperature and then fuel is injected. So we're going to be looking at spark ignition in the next video, followed by compression ignition when we discuss diesel cycles.